Welcome to October's MIDAS Expert webinar. Today we'll be focusing and presenting on the effects of long-term deformations on geometrically complex bridges, presented by Percy Penafiel, a professional engineer from Nevada DOT. To the introduction to Percy, he actually is experienced in multiple structural designs for highway bridges, pedestrian bridges, railroad bridges, as well as drainage structures, and structural supports for highway signs, luminaires, traffic signals, and toll gantries. He had experience with portal tunnels, soil nail walls, tieback walls, MSE walls, CIP retaining walls, and sound walls. He has obtained his construction experience reviewing and approving submissions and submittals for RFIs, NCRs, NDC, FDC, and any other coordination during construction. He has worked with the bridge load rating and dimensional vehicle permits. He has been an active presenter and a user of ours for quite some time now. And what I'll do is now bring the presentation over to Percy so he could get started with his presentation. And again, if there are any questions, please utilize the chat box to indicate any questions that you may have. But for now, I'm going to ask Percy if he can actually test his mic and his audio as well as his visuals to make sure that there's no problems. Percy? Percy, I think you might be muted as well.
Okay, can you hear me now?
Perfectly. Excellent.
Okay.
All right, and we see your screen.
Okay. Thank you for the introduction. Good afternoon, everyone. I am happy to be here sharing my experience and knowledge on this subject about effects of long-term deformations on geometrically complex bridges. This bridge subject to study is located in Las Vegas, Nevada, the intersection between I-15 and Desert Inn Road. The bridge name is structure H2011 Desert Inn grade separation over I-15. This bridge was built in 1995. It's a cast-in-place post-tension concrete box girder. It has three non-balanced spans with variable skew, horizontal curve, non-parallel girders, variable depth, AV typical.
Percy, I'm sorry. Would you mind hiding the control panel on the bottom? Oh, I think you just did. Thank you.
I just did. Yes, I just did.
Thank you.
Thank you. In order to prepare my model, I have to look at the contract plans. So I'm going to browse some of the sheets that I use to prepare my model. What you can see right now is the plan view of the bridge. I highlighted the skew, so see how the skew angle varies at different locations. And also notice that at the abutment 1, which is where my mouse is right now, the wing walls are parallel to the alignment. But on the abutment number 2, where my mouse is right now, the wing walls are parallel to the freeway I-15. On the elevation, you can see the span lengths. As you can see, they are different. Span 1, span 2, and span 3. Here you can see the typical sections. In red, I circle in red the location where the variable of the depth of the structure varies, but in general is AV typical. This happen only at a location where there is a flare. So it's between the pier number 2 and abutment number 2 is where this happens. Also, I just mentioning, I have to notice also that the column is a variable column section. As you can see, it flares from the bottom to the top, and the foundation is a spread footing. This is the framing plan. You can tell there are two horizontal curves, radius R1 between abutment 1 and pier 2, and there is another horizontal curve with radius R2 between pier 2 and abutment 2. And at every location the radius varies, so there is a table that you can see to locate every girder. Here you can see the Prestessin diagram, the jacking force, the long-term losses, the required jacking force, the friction coefficients. This is the strip seal expansion joint detail. The temperature where I was modeling this is at 70 degrees Fahrenheit with an installation gap of 158 inches. I was able to find shop drawings for this expansion joint. Uh, this detail was provided by D.S. Brown Company. We can see the gap, the initial gap at 70 degrees was 158 inches. The next thing that I'm going to show is some pictures from the inspection report. These bridges are usually inspected every 2 years. It was noticing some longitudinal cracks in the deck. This picture on the left. On the photo number 6, at abutment 1, it was noticing spalls and cracks at the shear key. On the shear key number 5 in abutment 1. On the photo number 7, it shows some failures of the seal, the joint seal. On photos 11 and 12, it shows cracks at the wingwalls on abutment number 2. There are also some deformations that they were noticing since 2010. Every 2 years, the gap at the barrel rail on the north side and south side of abutment number 2, it was moving very, I mean, every year was noticing increase in the openings. I was able to verify this in Google Maps. In the abutment number 2, you can tell this circle in red. I highlighted the location of the shear key that the inspection report is mentioning. This is the only shear key actually failed because the other ones are still in good condition. And also on this, there is a crack. You can see here there is a, where my mouse is pointing, there is a crack here. This was not noticed in the inspection report. On abutment number 2, yeah, we can verify the inspection report shows these wing cracks at the wing wall. These wing walls are actually facing the freeway. On January 2022, the inspection crew went to the field to measure the joints. It was found on this bridge on the abutment number 1, where my mouse is, the gap, the joint opening gap was measured at 3.78 inches on the south side. And on the north side was measured 3.5 inches. There is a small difference between the south side and the north side, but on abutment number 2, it was measured on the south side was almost 5 inches, 4.15/16. On the north side was measured 7.25 inch. So there is about 2 inches difference between the north and the south. Now I'm going to start talking about the MIDAS modeling. Due to the complexity of the geometry, um, I decided to draw this in CAD, specifically MicroStation. So for me, it was kind of easy to do the drafting in MicroStation, and then there is an option in MicroStation to export that to a DXF format. Once the file is exported to a DXF format, I can go to MIDAS, and MIDAS has an option to import a DXF file. I just wanted to note that when importing a DXF file, the length of the units must be identical with the unit using the MicroStation or the CAD software that you are using. I'm going to talk also about the material properties, the section properties, the supports, and the load cases that I developed in MIDAS. What you see in the screen is the actual MicroStation file that I use to create my model. All the drafting are basically using lines. So one thing that I have to notice is that um, we need to create some levels in MicroStation, and those levels are here. I'm showing a list: frames, joints, shells, grids, planes, a solid. If we want to create a final elements, shells, we can use these options and create that. But in this case, I'm just planning to use a grillage model. I'm not using shells elements. So these are just lines connected each other, following the geometry, the complex geometry that I mentioned in the contract plans. So once I create all the drafting in the level frames, then I am able to export that in MicroStation, go to File, Export, and select the option DXF. So once that is done, um, I go to MIDAS, and then in MIDAS, in the I click on where the C is. I select Import, and I select AutoCAD DXF file, and then I browse the location where the file is. In this case, is called H2011 Desert DXF file, which is the one that MicroStation created. I select Open, and when I select Open, I have to tell MIDAS what layer I use to create the elements in. So in this case, I use frames, so I select frames. So whatever I select is going to be moved to the right side. So then I click OK, and MIDAS will generate the model that I created in MicroStation. I'm going to talk now about defining material properties. For this specific bridge, I create 3 materials, where you can see where my mouse is. There are the first one, the ID number 1, represents the concrete or the superstructure. The number 2 is the the tendon uh, that I'm going to use for the post tensioning, and the number 3 is for the columns. Now I'm going to talk about defining the section properties. MIDAS has an option to use a PSC, which represents a pre-stressed concrete box. For the all interior sections, I use the option PSC I, as you can see here, where my mouse is. So this option creates all the interior girders. And for the exterior one, I use the option PSC H. Here I'm showing an example how I create a girder number 1. It's a PSCH option, and it's very straightforward. We can just input all the dimensions of the deck, the web. Now I'm going to present the definition of the supports. The supports in MIDAS, I go to boundary tab in the MIDAS and select define supports. For this study, I assume only vertical support. That's what I check. If you see my mouse here on the left, I check the option DZ, which just restrain the vertical movement. The other are free to rotate or move, because I want to see how this structure is going to behave. And here I'm showing the boundary conditions for the columns. I assuming fixed. It's a spread footing, so I assuming all the displacements and rotations are fixed. All these, because it's a spread footing and all the points are connected, so I am assuming they are not going to move and rotate. Following, I'm going to show the load cases that I created for this study. Only 3 cases I'm just considering. The first one is the dead load, which is essentially the self-weight. I am not considering additional dead load due to overlays or barrel rails, just only self-weight of the bridge. The second load case that I'm considering is the pre-stress. And the third case is the temperature. To define the dead load, we go to the main menu, we select load, select static loads, and select self-weight. Because all the geometry is already input, we just need to provide a -1 number, which represents the direction of the vertical axis in the negative or downwards, going the downward directions. The next case is the temperature. In order to define the temperature movement, we need to define what is the initial temperature. So in order to do that, we go to the main menu, select structure type. There we have the options to input the initial temperature. In this case, for this study, I am assuming the bridge was built at 70 degrees Fahrenheit. So I click OK. With that, then the next step is to define what is the final temperature. So according to the code for this concrete structure, or we can go through maximum 100 Fahrenheit for expansion or 30 Fahrenheit for contraction. Since I'm going to study the shrinkage and creep, I'm going to study the 30 Fahrenheit final temperature because it's the most critical in combination with shrinkage and creep. And that's what I do. I go to loads, temperature pre-stress option, and I select the final temperature 30. The next stage I'm going to show is the pre-stress, how to input the pre-stress load. So again, I select load in the main menu, select temperature pre-stress, and then there are 3 steps in order to do this. The first one is tendon properties, then tendon profile, and finally tendon pre-stress is where you input the actual force, the jacking force. So starting with the tendon property, um, we typically, well, for this example, I use the 27 strands number 6. It could be used a different one, but I don't have the shop drawings how this actually was built. So I am assuming it was used 27 strands number 6. It's a tendon type post tensioning. Then I select the material which I created previously, the tendon. These are the properties of the tendon. The total area of the 27 strands and the drag diameter, and then to calculate the relaxation coefficient, I use the Magura method, and 45 is for the pre-stressing loss. Then these are just the values of the ultimate strength of the tendon, the yield strength, the friction factors for curvature, and select what type of bond is this bonded or unbonded. This is bonded. And then these are the values for the anchorage slip. After that, I input all this information and click OK. And then I go to the next step, which is defining the tendon profile. For the tendon profile, we have a total of 14 girders, and every girder is going to have its own profile, right? So I got this from the contract plans. It's kind of a little bit tedious to create this. So what I did is I create a Excel spreadsheet with all the coordinates of the tendons. So you can notice that, I mean, these sharp angles can be improved, adding more points. So just for this particular study, I just make it simple. I didn't create too many coordinates on this. But creating all this spreadsheet can alleviate a lot of work, because once all these profiles are defined, we can just select, copy, and paste. For example, I'm just picking as an example the girder profile tendon, and just paste it directly to the MIDAS, so that that will create a profile as you can see here on the screen. So I have to do, for every single girder, I have to do the same, copy and paste, and it will draw the tendon at each girder. And finally, the last step is input the post-tensioning force. So there are 2 methods. We have to do that in every girder. So there are 2 methods how to input that. Is one is providing the stress, or just use the force directly. So either way, it will convert that to stress or stress to force. So for this particular case, I just select stress, and we usually the jacking force cannot be more than 75% of the ultimate. So that's the value that I input here. So this gear, every gear is going to be jacked from both sides. So that's why I select the option both. So yeah, with that, I have basically all the information of the load cases. Next, I'm going to talk about the creep and shrinkage. So the creep and shrinkage, in order to do that, I have to go to properties in the main menu, go to properties and select creep and shrinkage. And then I have to define a time-dependent material. In this case, I call it CS, just simplify creep shrinkage. After I create this, I have to tell the software what code I'm going to use to create this material. I select ASHTO. There are many other options there, but for this particular study, I select the ASHTO code. These values can be calculated for a specific bridge. Let's say the volume surface ratio can be calculated for each specific bridge, but typically it's around this number, 6 inches. The age of concrete at the beginning of shrinkage, I am assuming 7 days. This can be adjusted a little bit. This is the compression according to the contract plans that is specified. What we can see is clicking the show result, we can see how the diagram of the creep coefficient varies along the time. The maximum value is 1.8. We can see the diagram for the shrinkage strain coefficient to a maximum 7 to exponential to the -4. So once we create a defining time-dependent material, what we need to do is select what materials that we define at the very beginning. We defining all the materials, which one is going to be a time-dependent material. So for this particular study, the number 1 is representing the you see my mouse here. The number 1 is representing the superstructure, and the number 3 is representing the concrete for the columns. For this specific case, I'm just using the superstructure. I'm selecting the superstructure material to be as a time-dependent material. So this will link the material that I created to for the dependent material with the material that I create to define the properties of the superstructure. So now I'm going to talk about the construction stage. So this is required. That's what I put in red circle here. This is required to evaluate creep and shrinkage. There is no other option. We have to create a construction stage in order to evaluate creep and shrinkage, since this is going to be depending on time. In order to do that, I go into load, the main menu load, and I select construction stage. Then select define construction stage. For this particular example, I consider 3 construction stages. The construction stage number 1 will represent the construction of the columns. I am assuming a duration of 90 days for the construction of the columns. The construction sequence number 2 represents the construction of the superstructure. I am assuming 90 days also for the construction of the superstructure, and finally the construction sequence number 3, which will represent the time where the post-tensioning is applied. I am assuming it will be acting up to 10,000 days, so which is more or less the age of the structure until now. So if I for this construction sequence number 1, the duration, as I said, is 90 days for the construction of the column. I select the elements that are going to be involved in this construction 1, and this is the column elements. Then I have to specify what is the boundary conditions. The boundary conditions is fixed. And finally, what loads are going to be applied. Applying this sequence is the self weights. So I select the load, the tab load, and I select the self weight. Whatever I select, it goes immediately to this box on this side. Second is the construction sequence number 2, where is the superstructure. Again, I have to define the elements that are involved. In this case, I select all the superstructure elements. This is a group that I create with involved all the girders, diaphragms that are included in the superstructure. The boundary conditions, these are the supports at the abutments. So I move it from this list, I move it to this side, and that's why we see here superstructure supports. Finally, defining the construction sequence number 3 is where I define the post-tensioning. So the post-tensioning was on this side, and I move it to this side, so it's going to start acting after the construction of the superstructure is completed. So we apply the post-tensioning force, and it's going to start acting for 10,000 days as is specified here. I'm going to now show the analysis and results of this study. As you can see, this is the final deformation in MIDAS. I just wanted to note that you can see the results according to the construction stage 1, 2, or 3, or post CS represent the final where all the other loads are acting. So for this specific study, I just wanted to see the shrinkage and creep deformations. So as you can see, CS summation means that it's adding all together, it's adding the post-tensioning, the creep, and the shrinkage all together. And I just only want the deformations in the XY plane. I check the undeformed, which is what you can see in the gray. In the gray line is the original structure, what is shown in gray. And I also check the values because I want to see how much is deforming. So these are in inches, units of inches. As we can see, the structure is moving kind of to the north, right? And this deformation is, this is a combination. This is not just in the y direction. This is the resultant, the total resultant deformation. And this deformation, I think, is the one that is causing this wing wall to crack. And on the other side, on the south side, in abutment number 1, there is also a small deformations towards the south, and that is probably causing these cracks on these shear keys. As you can see here in the photo, that I showed previously in the inspection report. I think that is the reason of those cracks. Somehow the superstructure is pushing the shear key this, I mean, to the left, in this photo to the left. So here I'm just showing the deformations for in every case. This is the deformation due to the post-tensioning only, and this is the deformation due to the creep. These are the deformations due to the shrinkage. And then for the evaluation of the temperature, since that is not part of the construction sequence, so here where I'm highlighting here with my mouse, I need to select pose CS. So you notice for the other deformations, I have to select construction sequence number 3. But for the temperature, which is a final load, I have to select pose CS. Here I'm showing a table, a summary table with the results. I just wanted to talk a little bit about this. On abutment number 2, the MIDAS result, which is where my mouse is right now, the number 6.885 is the deformation on the north side at the joint on abutment number 2, and the 4 inches is on the south side of the abutment number 2. It it correlates pretty good with the field measurements. So we notice that there is a larger gap at the north side of that joint compared to the south, so it correlates pretty good. But I cannot tell about the abutment number 1. The field measuring is about kind of, there is a 2 inches difference with the MIDAS result. I cannot explain why this happened. Maybe there is some restriction to move at the abutment number 1, and that's probably the reason of the cracks of the shear key. So and also I'm comparing these results with Caltrans. Caltrans has a simplified method. What you can see in the screen right now is a table that Caltrans developed to calculate joint movements. So it includes everything: shrinkage, long-term deformations, and temperature. So for this specific bridge, I calculate these values using those using that table, and apparently these results correlate a little bit better with the field measurements, 3.56. So it's very close to the field measurements on the abutment number 1. But for the number 2, it is not correlating. So I guess that the Caltrans formulas are more important to use, or are able, I mean, I guess that can be used for bridges that are regular, with geometry, with very simple geometry. Maybe these Caltrans formulas will work better. So this concludes my presentation. Thank you.